Today we are going to be talking about the concept of mesh analysis. So nodal analysis, which we covered last Friday, was an analysis technique in which we applied multiple iterations of Kirchhoff's current law in order to solve for all unknown voltages in a system. Mesh analysis is multiple applications of Kirchhoff's voltage law in order to solve for all unknown currents in a system. We are going to take an algorithmic approach to this analysis technique, just like we did with nodal analysis on last Friday. Because the algorithms are so similar, I'm probably going to go through this a little bit faster so that I don't talk for 90 minutes straight like I did on Friday. Okay. So let's look at our first circuit. And we are going to start with circuits that do not have current sources, and then we'll move to circuits that do include current sources after we figure out what the general rules are. All right, so this is our circuit that we are going to be analyzing, okay? Our first step is to identify our meshes. Does anybody remember what a mesh is? We talked about this on literally the first day of class. So a mesh is just a loop that doesn't contain any smaller loops. So this particular circuit contains exactly 3 meshes. We are going to have, let's change the color here. This mesh this mesh, and this mesh. Okay. Since those are the smallest loops that we can make that do not include any smaller loops. Step number 2 is to assign our mesh currents. And realistically, you can actually just combine steps 1 and 2 together, and I'll show you what I mean by that. So the way that I've drawn these paths, I'm just going to put the head of an arrow on here, and I'm going to call this mesh current IA. This will be mesh current IB. And this will be mesh current IC. I have drawn all of my mesh currents as if they are flowing clockwise around their respective meshes. That's just the way that I am used to doing this. You do not have to draw them all clockwise. You can draw them counterclockwise. You can draw them some combination thereof. I would argue that being consistent with the direction that you draw your mesh currents will help you out in the long run. In this clockwise fashion, what we will find is that when we are applying Kirchhoff's voltage law around mesh A, all of our IA terms will have a positive sign, and all of the terms for the other mesh currents will have negative signs. That's only true if you draw all of your mesh currents in the same direction. If you have some clockwise and some counterclockwise, you might find that you have terms where you have IA plus IB and all that kind of stuff. And it gets confusing, and in my opinion, it's hard to follow. So I would highly recommend that you draw all of your mesh currents either clockwise or counterclockwise, but it is not required in order to get the right answer. It's just harder to find mistakes, if any are made, if you choose to mix and match your mesh currents. The next thing that we are going to do is we are going to express our controlling variables in terms of our mesh currents. So in this particular circuit, our controlling variable is the voltage Vx, which is the voltage drop across the 4 ohm resistor in the bottom middle branch of this circuit. So what we are going to do here is use Ohm's law to figure out how to express that voltage drop in terms of our mesh currents. Well, Ohm's law tells us that it is the total current flowing through the 4 ohm resistor, which we'll need to figure out, multiplied by the resistor value gives us the voltage drop. So I'm going to start with the resistor value, okay, 4 ohms. I think that part we can all agree on. Now here's where things get slightly more complicated, okay? The total current that's flowing through the 4 ohm resistor is going to be some combination of IA and IC, because that 4 ohm resistor is shared between those two meshes. So what we're looking for is the mesh current that's flowing into the positive polarity terminal minus the mesh current that's flowing into the negative polarity terminal. So which of our mesh currents, as they go around their clockwise path, flows into the positive polarity terminal of the voltage Vx? IA. Which of the mesh currents, as it's flowing around its clockwise path, flows into the negative polarity terminal of the voltage Vx? IC. There we go. We have now expressed our controlling variable in terms of our mesh currents. What if instead I had a controlling variable, let's do it, I guess, in this color. IY. How would I write my expression for IY in terms of my mesh currents? IA minus IB, the exact same thing we did for the current flowing through the 4 ohm resistor. It's always going to be the current flowing in the same direction as our controlling current minus the mesh current flowing in the opposite direction. So IA minus IB. All right. So because we don't have any current sources in this circuit, we are ready to move on to our next step. So step number 4 here will be to write KVL equations for each, that's not how you spell each, mesh. So we have 3 meshes. So we're going to have KCL at mesh 1, And I'm going to scroll up here and I'm going to explain what this process is. Excuse me, did I write KCL or KVL? Should be KVL. So I'm going to write these KVL equations exactly like I've done every other time we've written a KVL equation in this class. I start at the bottom left-hand corner and I just follow that path, okay? So anytime I see a voltage source, if I see the negative polarity terminal first, I write negative the voltage. Anytime I see a resistor, I assume that IA is flowing into the positive polarity terminal and any opposing mesh current is flowing into the negative polarity terminal. So as I start from the bottom left-hand corner here and follow my path up, the first thing I see is negative 10 volts. The next thing I see is the 9 ohm resistor. The only mesh current that's flowing through the 9 ohm resistor is IA. So I will have plus 9 ohms times IA. And the next thing I see is the 2 ohm resistor. There are 2 mesh currents flowing through the 2 ohm resistor. IA is flowing down. IB is flowing up. Since I'm writing my KVL equation for mesh A, IA should be the thing that gets the positive sign. And because IB is in the opposite direction, it's going to get his negative sign, which is exactly what we saw when we were expressing our controlling variables in terms of mesh currents, okay? So when we're following mesh current IA around, IA should get the positive sign and anything in the opposite direction of IA should get the negative sign. So that's going to be 2 ohms IA minus IB. Then we see our 4 ohm resistor. IA minus IC. And then finally down here at the bottom, we have a 5 ohm resistor where IA is the only current, mesh current flowing through it. Set this equal to 0. Let's call these A and B so that I'm being consistent with what I have on the picture. All right, so who wants to tell me what our KVL equation for mesh B should look like? Sure, Jacob.
First, you have the 2 ohm resistor
Okay,
times IB minus IA.
absolutely right. You want to keep on going or you want to hand it off to somebody else? Daniel, you raised your hand a moment ago. What's the next term? Absolutely correct. Any volunteers for the third term? Sure. Mm-hmm. Yeah. So we are assuming that the mesh current that we're following is always going to be flowing into the positive polarity terminal when we're writing these equations. So you're 100% correct. In our first equation, we assumed that the positive polarity terminal for the 2 ohm resistor was at the top. In our second equation here, we are assuming that the positive polarity terminal is at the bottom, such that the mesh current that we're following around our path is always flowing into the positive polarity terminal. All right, third term. Ryder, sorry. 7 ohms times IB. And then William, I believe you had your hand up. Can you take us home with the fourth term here? Yeah, so negative 3Vx. Minus 3Vx is equal to 0. Wonderful job. And now we have KVL at mesh C. Who wants to start us off? Hannah. Thank you very much. Wonderful. 4AC minus IA. So if we could have additionally written that as negative Vx, okay? But when we are expressing with our mesh currents here, the Vx is entirely unimportant. Now, we could call it negative Vx and then plus the remainder of the stuff. But in terms of our mesh currents, that's still going to wind up being 4IC minus IA. Next term. Mason, how are you feeling today? You're absolutely correct. Plus 3 Vx. And our next term, Hayden, got any thoughts? What happened to the 8 ohm resistor? Yep. 8 ohms and then followed by 6 ohms. And if we were feeling real squirrely, we could observe that those two resistors are in series and combine them together into a single 14 ohm resistor if we wanted to. So that's IC plus 6 ohms times IC is equal to 0. All right, so at this point, we have 4 equations and 4 unknowns. We could substitute in our relationship for Vx if needed, or if you took my advice and bought the calculator I told you to, we're ready to rock and roll. So at this point, it's just throwing crap in our calculator and moving forward. So you guys ostensibly all know how to do that at this point because you've been working on your nodal analysis homework. Now let's break things by including voltage sources, or excuse me, current sources. So instead of explaining why with a small example here, we are just going to include a circuit, or we're going to analyze a circuit that has a current source in it and see how we need to adapt our algorithm, okay? So I am hopefully correctly making the assumption that you guys know how to use your calculators at this point. If you happen to not, please let me know when we get to the in-class assignment portion of the class, and I will help you figure stuff out. All right, so this is our circuit that we are going to analyze here. I am going to lump steps 1 and 2 together. And we are going to identify and label our mesh currents. So I am going to call this one IA, this one IB, this one IC, and this one IB. Our next step will remain the same. We will be expressing our controlling variable in terms of our mesh currents. In this case, our controlling variable is the current IX that is flowing up through the 5 ohm resistor. So somebody tell me how to write that current in terms of my mesh currents. Perfect, Brody, thank you. All right, so here's where things are going to get slightly different. So when we were performing nodal analysis and we had voltage sources, we had to write voltage relationship equations. When we are performing mesh analysis and there are current sources, we will have to write a current relationship equation for each current source, okay? So that's our new step 4. CS here just stands for current source. So we have 2 current sources in this circuit. The 5 amp source is what I'm going to refer to as an interior current source because it's inside the circuit. And a 6 amp current source is what I'm going to call an exterior current source because it's on the perimeter or the edge of the circuit, okay? So let's start with the 5 amp source. 5 amps will be equal to the mesh current that's flowing in the same direction as the 5 amp source minus the mesh current that's flowing in the opposite direction of the 5 amp source as those mesh currents flow through the branch containing the 5 amp source. So which mesh current is in the same direction as it flows through that centermost branch? IC. Which mesh current is in the opposite direction? IA. So we have simply 5 amps is equal to IC minus IA. Anytime we have an interior current source, it's always going to be a combination of mesh currents, and it will always be exactly 2 mesh currents. Anytime we have a current source on the perimeter of the circuit, it's only going to be expressed in terms of a single mesh current because there's no opposing mesh current flowing through it. So in this case, we would have 6 amps is equal to what? ID. That's it. If the 6 amp current source were direction up, what would we have had? Negative ID, right? Okay, so we're now ready to move on to our writing of Kirchhoff's voltage law equations. So before we write anything down here, I want to talk our way through about what's about to happen, and then we'll talk about how we are going to fix it, okay? So if we wrote a Kirchhoff's voltage law equation for mesh A, through the 10 ohm resistor, everything's fine. Through the 4 ohm resistor, everything's fine. Through the 2 ohm resistor, everything's fine. And then we hit that independent current source. Doesn't particularly matter that it's an independent current source. Any current source is going to cause this problem, right? So our KVL equation is an expression of the sum of the voltage drops around that path. Well, whenever we have a current source, we know that the current source is providing some amount of current regardless of what the voltage drop across the current source is. So we do not have any relationship between the voltage drop across the current source and our mesh currents, okay? Then we'd hit our 3 ohm resistor and everything would be fine. Well, as we follow mesh current IC around, we run into the exact same problem, but the current's flowing in the opposite direction. So we are going to do something very similar to what we did with nodal analysis whenever we had a voltage source. We are going to create a super mesh. And what our super mesh is going to be is the smallest possible combination of meshes that avoids us writing a voltage drop across that current source. So that is going to look like this. So we're following mesh A exactly until we hit the branch with the current source in it. And then we're going to come down here to avoid taking the voltage drop across the current source. And then we're going to come over here. This particular super mesh avoids the 2 ohm resistor as well. Some of you may be thinking, oh, well, how does this work if we just get to arbitrarily throw away the voltage drop across the 2 ohm resistor? Well, the voltage drop across the 2 ohm resistor is obviously just 10 volts because there's 5 amps of current flowing through it. We're not neglecting anything. That's already a known quantity as far as we're concerned. So anytime, actually, let me rephrase that slightly because I'm going to show you a case where it won't work in a moment. The overwhelming majority of the time, whenever we have an interior current source, we will have a super mesh that contains, that's going to give us a Kirchhoff's voltage law equation and a current relationship equation. Since this particular super mesh is composed of 2 meshes, we should expect to get 2 equations from it. We already have one of them. It's our current relationship equation for the 5 amp source. Our next equation is going to come from writing Kirchhoff's voltage law around this super mesh. So step number 5 will be write KVL equations for all super meshes. So we are going to be following that light purple path. Okay. So starting from the bottom left-hand corner of mesh A, the first thing we see is the 10 ohm resistor. So we're going to have 10 ohms times IA. And this is super mesh A. What's the next thing we see? All right, and what's the current flowing through the 4 ohm resistor expressed in terms of our mesh currents? Exactly right. 4 ohms times IA minus IB. What's the next thing we see? The 5 ohm resistor, okay? So now we've switched over to where we're following mesh current IC around its clockwise path. So what's the voltage drop across the 5 ohm resistor? Yeah, so 5 ohms IC minus ID. then we see what? Minus 2ix. Then we have the 3 ohm resistor, which is going to carry a total current of IA minus IB. Thank you. Set this equal to 0. All right. Stop giving me this error step. Give me just a second. I need to save this and then restart this program, or that stupid thing is going to pop up over and over again. All right. Step number 6. Write KVL equations for all meshes, I guess all remaining meshes that do not contain perimeter current sources. So why I have to make that particular distinction is that if we try to write a KVL equation for mesh D, we literally can't do it. That 6 amp source prevents us from writing a KVL equation because we just have the voltage drop across that current source and we have nothing whatsoever to relate it to. So we have that one mesh there and we have no equation for it, except that we wrote it when we wrote our current relationship equations, okay? So that current relationship equation, 6 amps is equal to ID, is the only information we need to know about mesh current D in order to solve this system. Writing a KVL equation there, A, is impossible, and B, wouldn't give us any new information anyway. Okay? So the only mesh that we don't have an equation for is mesh current IB. So somebody tell me what that equation is going to look like. So -4 volts. Let me scroll down here. KVL, sorry. Daniel, keep going. And equal to 0, right? Yep, only the 3 terms. All right. So in this particular circuit, we have 4 unknown mesh currents, IA, IB, IC, ID, as well as the controlling variable IX. So we're expecting to get 5 equations in order to solve this thing. 1, 2, 3, 4, 5 equations. We have enough to solve. Obviously here, we could take ID and everywhere we see it, replace it with 6 amps. Everywhere that we have IX, substitute that in, and this would reduce down to a 3 equation, 3 unknown system that any and all of our calculators should be able to take care of. Or we could solve it using MathCAD or whatever the hell we felt like. So again, we've hit the point where we would just solve this system of equations, which you all should arguably know how to do. Now let's mess with things slightly further, and that'll be the end of me talking for the day. So the next thing that I'm going to talk about here is effectively just a continuation of this, but it's a special case that we need to pay attention to. So in this particular circuit, we had a super mesh, and then we had a separate perimeter current source. What would happen effectively if that 5 amp source and that 5 ohm resistor were to switch places? There would not be a super mesh that we could actually write a KVL equation around. So let me illustrate that specifically here, okay? So I'm just going to draw a more simple circuit here that we're just going to look at very briefly. So let's say that we had the following circuit and we were going to attempt to do mesh analysis. Let's not even make it that hard. Let's not put any dependent sources. That's not adding anything to the discussion. It's just making this take longer. All right, so this is our circuit that we're going to analyze. Obviously, this is a 2-mesh circuit. So let's call this IA. Let's call this IB. We don't have any controlling variables. We do have current relationships. So our current relationship equations are going to look like what? So 2 amps is equal to IA minus IB. Four amps is equal to negative IB. We're done. We couldn't write a KVL equation around literally any path in this circuit without having to take a voltage drop over a current source, okay? We have 2 meshes. We have 2 equations. Why do we need any more information whatsoever, okay? Now, I gave you something this simple purely to illustrate what would happen. In your in-class assignment problem, I believe your 3rd problem, it takes it one step further. There is also another loop that you will have to write a KVL equation for. But effectively, if you have, I'm trying to think of how to describe this. We have an interior current source, so our gut reaction would be to create a super mesh that encloses that interior current source. But if that super mesh contains a perimeter current source as well, you're only going to have current relationship equations to deal with, because there is literally not a KVL equation that you could write that would avoid taking the voltage drop over one of those current sources, okay? This isn't something that you're going to see often, but I want to make sure that you're aware of it because you're definitely going to see it in this in-class assignment, and you're definitely going to see it at least once in your homeworks. Daniel. The current relationship equations are where it's going to go. So for instance, let's see, I have to be careful about what I'm going to put here or I will break physics or whatever. I was just going to arbitrarily turn this 10-volt source into a 10 amp source, and then we could have, we could have 3 equations. The potential issue there, if I would be all the current flowing in has to equal all the current flowing out. Effectively, I don't want to just make up numbers and then have it not work out and break the rules there. But the short answer to your question is the current relationship equation should be enough. Now that's if I'm saying that assuming that the person who's writing the equation or writing the problem is as meticulous as I am about making sure that intelligence theorem and all that kind of good stuff actually get satisfied every time so that everything works out neatly and nicely. But you shouldn't have any issues like that in any of the homeworks here or any of the tests or anything. So, all right, so that's mesh analysis. I've wrapped it up in 45 minutes, so about half as long as it took me to do nodal on Friday. In-class assignment time, if you have any questions, I'd be happy to answer them.